In this toolkit, we're going to be using equations, looking at the equations, and then graphing them and determining whether they are linear or nonlinear. And we're thinking about this statement here. I can explain why the equation y equals mx plus b is a linear function. So your explanation is going to be in your graph and also in the way that you're describing that equation. So first we're going to write it here at the top, y equals mx plus b. And I'm going to use the same colors that I always use. I'm going to color this blue. And if I'm coloring that blue, we should know by now that the blue color is always standing for rate of change. So this has to do with our rate of change. Rate of change. And then I'm going to color my B green, and we know that, couldn't see that there, the B is standing for our y-intercept. And so we have different kinds of, like why is it B? Why is it M? Those are just placeholders for you to put in your y-intercept and your rate of change. You can think about B as the beginning number that it starts with, the beginning number is your y-intercept, and the M standing for the number you're multiplying by, or the rate of change, the multiple. All right? And as we work through this, I'm just going to, again, continue to use my colors to identify what makes this linear and nonlinear. Something that is linear on a graph is always a straight line. Doesn't matter where the line is, it just has to be straight. So that is the identifying piece there. So I'm going to write a note about that as well and say a graph, or a linear graph. A linear graph equals a straight line. All right? Coming back to that every time. We have to decide as we draw these out, are they straight lines? Well, it's hard for us to look at an equation and go straight to a graph, but we do know how to do inputs and outputs on tables. And so we're going to go from the equation, we're going to make a table, and then we're going to graph it. You only need a couple points to make your table and graph it because you're going to be connecting the dots. All right? So you really only need 3. You have to have more than 2, but you can get by with 3. I'm going to start with this first one on the left. It says y equals 1/2 x minus 5. And knowing that we're putting a place value in for x. So might as well start with 0, right? The equation for this is y equals 1/2 times 0 minus 5. Well, 1/2 times 0 is 0, minus 5 is negative 5. And then as I find another value, let me do 1. Y equals 1/2 times 1. So let me write this out. This was 1/2 times 0 minus 5, and that equals negative 5. This is 1/2 times 1 minus 5, because x has been replaced with 0, and now with 1, because there's 1. And that gives me negative 4 1/2. And I'm going to do another one, 2, and I'm going to say that that is going to be 1/2 times 2 minus 5, and that's going to be 1/2 times 2 is 1, minus 5 is negative 4. I'm going to plot these 3 points on this graph. I've got 0, negative 5, there's that point. I've got 1 over 1 and down 4.5, there's that point. And I've got 2 down 4, so I'm over 2 and down 4. There's that point. And if you look, it's really hard for me to determine whether that's linear or nonlinear because they're so close. So I'm actually going to take another point like maybe 8 and find out what that value is. So I decided that as I made the table, it's too close. I can't decide because what's really happening over here and here, I'm not sure. 8. And I'm going to do 1/2 times 8, which is 4, minus 5 gives me negative 1. I'm going to go over 8, down 1. Okay? And as I look at this, the graph line is looking like this. And as I continue back, I might do -4 as an x. So there's -4, and I'm going to find out where it falls here on -4. And that's going to be 1/2 times -4. -4 times 1/2 is -2 minus 5. -2 minus 5 equals -7. That coordinate pair is -4 and down 7. And as I see, this equation is in fact linear because as I connected my points, it was a straight line. If I were to look at this, I would see that every time I'm doing the same pattern to get to my next point, I'm going up 1 square and over 2, up 1 and over 2, up 1 over 2, and that's going to continue. And I'm going to see that that's showing up right here as 1/2. Okay, I'm going up 1 and over 2 each time. There's my rate of change. There's my rate of change. It's going up at a constant 1/2 every time, making it straight. So it happens to have a y-intercept of -5, and there's that -5. Okay? So this is linear. I can explain why, because it has a constant rate of 1/2. It's increasing by, if we think about our rate of change is change of y over change of x. This is increasing by a change in 1 for the y every time the x is increasing by 2. Okay? That's making it linear. It's not increasing at increasing at a constant rate. The rate is not increasing, say for example, up 2 and over 1 and then doing something different, like for example, up 5 and over 1. That would give us a curved line if we were looking at that. Okay? Moving on to the next one. So we've got to decide if it continues to go down to this equation y equals mx plus b, where I can find the rate of change. The rate of change here was 1/2, and I can find the y-intercept, and the y-intercept here was -5, then it must be linear because that's going to have a constant rate of change and therefore make a straight line. So we're thinking, what's the rate of change here? Well, we know rate of change is change of y over change of x, and in this case it says x over 4. Well, what is x? How many x's are there? And in this case, there's an invisible 1. It's an invisible 1x. So I'm actually going to say 1x over 4 plus 2. And I'm just rewriting it so that we can start to see that rate of change. So that change of y is 1, that change of x is 4, and it's showing up right there. Okay? Change of y over change of x is 1/4, and we started with 2. Now this time I'm going to graph it straight from the equation, so you can see graphing it instead of going equation table graph. I'm just going to use the key features. And this said I'm starting at 2, so that means 0, 2. And I'll plot the table as we do this as well. 0, 2. So there's that starting point. And then it's saying I'm going to go up 1 and over 4. I'm going to go up 1, then over 1, 2, 3, 4. There's my new dot. I'm going to go up 1 and over 1, 2, 3, 4. There's my new dot. So it's like stair steps. I can work this backwards. Down 1, 1, 2, 3, 4. Down 1, 1, 2, 3, 4. We're going to end up with another straight line and therefore linear. And therefore the rate of change here is 1/4. Now how is that possible? I'm going to go back to putting in some inputs and outputs on this equation so you can see how that actually happened. We have that rate of change showing up 1 over 4, up 1 over 4, up 1 and over 4 every time. Okay? So the equation x for this point is 0 over 4 plus 2, right? 0 divided by 4, so nothing broken up into 4 groups is still nothing. So 0 divided by 4 is still 0, plus 2 gives me 2. I'm going to now have the input of 1, That's going to equal 1 instead of x, right? Instead of the x there, it's 1 over 4. It's 1/4 plus 2 is 2 and a fourth. So if I'm over 1 and I'm up 2 and a fourth, that's really hard to see. So let's look at this point here, 4, and it should give us the answer of 3, right? If I were to look at those points right there, I'm going to go 4. So what that is 4 over 4, which is 1, plus 2 equals 3. And there's that coordinate point. I'm going to check this point here, 8. So if I put in the input 8, I should get out the output of 4, right? Because that's where that value is right there. And so 8 is being inputted in for my x. 8 divided by 4 plus 2. 8 divided by 4 is 2, plus 2 gives me 4. Okay? And so we're seeing that if we graph that equation, it's straight. And continuing, this equation, the rate of change is 2. The y-intercept is -5. So using key features here to plot, I'm down 0, -5. This is telling me my change in my y over change in x is 2 over 1, because that is the rate of change. And 2 over 1 is the same thing as 2. Okay, so this is telling me my vertical change is 2, my horizontal change is 1. So from that point, that starting point, or B, that beginning point, I'm going to go up 2 over 1, make a dot. Up 2 over 1, make a dot. Up 2 over 1, make a dot. Up 2 over 1, make a dot, and continue that pattern. As I do that, I see again, I have a straight line, and therefore, it again is in the format y equals my m, which is my rate of change, times x, plus my y-intercept. Now remember, this equation could also be represented as y equals -5 plus 2x, and everything was just flipped, and it's still equivalent, and because it's equivalent, it's still linear. If I were to graph that or find coordinate pairs for that, I would end up with the same answers. Okay, so moving on, looking at this next one here. This looks pretty similar to this one up here, and we're going to see how they sometimes can be deceiving there. The only difference is numerator and denominator are flipped, and so what happens when we do that? Okay, making a table of this. X and y, and I'm going to put in the table 0. So I'm going to make that equation. That equation there is 4 over 0, right, plus 2. Well, anything over 0 is an undefined number, meaning it doesn't exist. You cannot break anything into 0. So in previous years, we've learned that you cannot divide by 0. It's not an answer. Right now, we know that is nonlinear. Nonlinear. What makes it nonlinear? The x is in the wrong place. It's in the denominator, and that means I can put in 0, and it's not going to work. Okay, so let's try another one. I put in 1. My equation here is 4 over 1 plus 2. 4 over 1 is 4, plus 2 is 6. I'm going to go over 1 and up 6. There's that point. I'm going to try the number 4, because remember, you can just pick any number. 4 over 4 plus 2. Well, 4 over 4 is 1, plus 2 is 3. So there's that coordinate point, 4, 3, over 4, and a 3. Right now we have 2 points. Well, we actually have 3, and it's already undefined. We know it's nonlinear because of that, but I'm going to show us on the graph how it ends up not being straight. I'm going to now pick the number 8. 8 over 4, 4 over 8, right, because the x was being replaced with the 8. 4 over 8 is 1/2 plus 2, that equals 2 1/2. I'm over 8 and I am up 2 1/2. And look, that is not straight. What that's going to end up looking like is something like that. If you were to collect all the little points in between, that's what it would look like. Okay? So therefore, because it is not straight, it is nonlinear, and we can see that when the x is in the denominator position, it makes it nonlinear. Moving on. we are looking at x being squared. In this case, again, I'm going to use some coordinate points so we can verify whether it's straight or not. And we're going to start with 0. And so in this case, we're saying 0 squared plus 1. Well, what's 0 squared? Well, it's 0 times 0, and 0 times 0 is still 0. Plus 1 is 1. The coordinate pair is 0, 1. And then I have, let's go with 2. 2 squared plus 2. Well, 2 times 2, or 2 squared, is 4, plus 2 is 6. So over 2 and up 6. And let's do 3. I'm going to do 3 squared, which 3 times 3 is 9. This is, the squaring is multiplying the base value to itself. So this is not 3 times 2, this is 3 squared, which is 9, plus 2 is 11. So over 3 and up 10, 11. It's hard to tell right now whether that's linear or not. It's looking kind of straight. So let's pull back and get a number like negative 2. Negative 2. So I'm going to look back here. So negative 2 squared plus 2. Negative 2 squared is negative 2 times negative 2, which gives us positive 4. Plus 2 is 6. Negative 2 and up 6. And we see right there, this is non-linear. It's actually going to look like this. Okay, it's not a straight line. Okay, so it is non-linear. And the last one is y equals 3x. Again, using a table, putting some inputs and outputs. And in all of these on the tables, you could also be using change of y over change of x to see if they simplify down to the unit rate like we've done previously, and see if they're linear that way. 3 to the power of x. Well, let's say, for example, 1. So that's 3 to the first power. Well, that means 3 just by itself, not multiplied to anything, which is 3. So that coordinate pair is 1, 3. And let's do the number 2. So that's 3 squared. So that's the same thing as 3 times 3, also known as 9. So over 2 and up 9. And let's look at number 3. So that's 3 cubed. And what that means is 3 multiplied to itself 3 times. So 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. And we're going to see that's way up here. And so it's way off. So I'm going to work my way back. And I'm actually going to go to, let's go with negative 1. So 3 to the power of negative 1. And if you were to calculate that into your calculator, you're going to end up with a number between 0 and 1. And it's going to be 1/3 right there. And your graph line is going to end up looking like that. And it's curved. And so when the x is in the exponent position, it makes it non-linear. So knowing when we look at equations, what we've seen is x is in the exponent, x is being squared, and x is in the denominator. All make it non-linear. I'm going to write that up at the top. So when the x was non-linear, equals x was in denominator. The x was squared, and the x was an exponent, all made them non-linear.